Please introduce yourself and briefly summarize your education and professional background.
Yeah, so first of all, thanks for having me. And my name is Joel Heidema. I'm a professional engineer, so I'm a PE. My background is in construction. I started in construction in the trades, and I worked as an apprentice carpenter for a couple years, and then I went ahead and got a bachelor's and master's in civil engineering at the University of Nevada here in Reno. And then after graduation, I worked for different structural engineers, and I also worked for a big contractor, Katera Construction, for a couple of years before they went bankrupt essentially. And then from there, I started my own structural engineering firm in 2018, working on the side, doing structural engineering and working for Katera Construction. And then when they filed bankruptcy, I just took it as a sign to go kind of full time as a structural engineer and run my own firm. And then from there, I've been running my own company. I previously was running a company called Cerebrum Solutions. And then last year, I merged with a colleague of mine that I've known for a while, and we created Palisade Engineering. So, overall, I've got about 20 years of experience in construction and engineering.
Okay, can you tell me a little bit more about Palisade Engineering and how you specialize in structural and seismic anchorage engineering for data center and mission critical facilities? Basically, some details about what that means.
Like I said, Palisade Engineering, we just started it with my partner, Paul Waite, about a year ago now. And, my background is been heavily in kind of multifamily and light frame construction. And right now we're seeing a lot of data center demand just because of the current climate. And Reno is actually in close proximity to the gigawatt fact or the gigafactory, right, which is a Tesla gigafactory. And then because of that initial investment that Tesla had done, it drew in a lot of other larger companies. And so there's a lot of local development going on with the data center stuff. And so, yeah, that's something we're pushing heavily into, and just trying to expand into that market as quickly as possible and provide resources for contractors and owners.
That sounds good. Obviously, we've all heard a lot about the data center boom, but can you describe it a little bit from just the engineer's perspective? I mean, from their viewpoint, like what's going on and how should engineers in particular look at this explosive growth?
Yeah, so there's two components to the data center stuff as it relates to structural engineering. There's essentially the shell design, so the building design, and that a lot of times is done by a separate engineer than what the engineer who works on these components that are inside the building. So because of all the racks and all the overhead equipment, there's a lot of weight inside the building that needs to get, self-supported or attached to the building somehow. And so what we're focusing on at Palisade is, a lot of times the whole shell is already done, and where contractors, especially contractors and electrical contractors mainly, they need a lot of support is all these heavy components that are going inside the building. So there's kind of those two components, and in the code, the component section is a different section than the building design section, and so that the calculations are different. Yeah, and so there's like engineering wise, there's so much weight inside the building that needs to be accounted for, and that whole infrastructure as far as like cost of construction relative to the actual shell. The electrical components that go in there are it's crazy. I think it's something like 60% or something of the cost of construction of the building, just because of all the racks and everything, and especially with the AI stuff coming out right now.
So how does an engineer learn about and find out the numbers on all of these components? Is that coming from, the original owner, or do you have to work with all the contractors to find out
Yeah,
all the details of the engineering requirements that you need?
yeah. So basically, the workflow is like this. We we're contacted, or we contact a supplier or a subcontractor to the GC, and the subcontractor is either electrical or an HVAC contractor, and then they also have subcontractors under them, so another sub tier, and these guys have the equipment specs that the owner, or like if the owner's NVIDIA, right, they have all their GPU racks, all of that equipment specs, that they have the weights, they have the geometry of these racks, and then they have where the anchors are, because all of this stuff is pre-manufactured already, right? And so basically we need the geometry to do the calculations of the rack, and then we also need to know where it's going in the building, because that determines how much seismic load is on the building. So like the higher up in a building component is, the more seismic load. Like if you think of a whip, like at the end of the whip, there's a lot of acceleration at the end of the whip. And so that's the same thing in an earthquake, is the building kind of essentially whips back and forth. So we need to know where the equipment is in the building, and we kind of need to know how they want to anchor it. And so from there, we just go to the code, ASC 722. That's the new code that came out recently, or a couple of years ago, but it's mainly what we're used here in this area. And then in that code, there's requirements that we go through the calculations. And there's a lot of coordination with the subcontractors on how they want to do it, what anchors they want to use. Like, yeah, there's a whole bunch of communication that needs to happen.
Okay, just to clarify, that code you mentioned, is that specifically for data centers, and does that cover all aspects of them, or is that just, kind of the structural design or the seismic elements, or can you give me a little bit more about that?
Yeah, so ASC 722 is it's basically the standard that's written for structural design, and it's adopted into the International Building Code. But it's where us engineers go to get the loading, where we go to get the code requirements for specific items that need to be installed. So it's for building design and for components and all of that. So like all these jurisdictions nationwide, they adopt the IBC or some portion of the IBC, and under the IBC is ASC 722, which is adopted. So it's a requirement that you need to use when you're doing buildings, basically when you're doing anything structural, because there's a lot of research that goes into the codes to make sure that the building doesn't fall over and kill somebody. And so that kind of leads into like a different thing about these data centers is, the building designer, they design for the building not to fall over and collapse. So there's, there's like the target is, less than a 10% risk of collapse for the maximum credible earthquake, essentially. So this earthquake that's going to happen, the big one, it's targeted that less than 10% of these are going to collapse. And so inside the building, though, we have to use that same code and make sure these equipment that's hanging off of the building or sitting on the slab doesn't fall over and kill somebody. And so that's where this seismic anchorage stuff that is one of our main products that we're trying to offer, is making sure that this thing is anchored properly so it doesn't fall off the wall or fall over on the ground onto somebody. So basically, if you think about it, you don't want anything heavy over your head in a seismic event. You want to make sure that thing is anchored properly, and that's why you need structural engineers to do these non-structural components inside the buildings.
All right, Joel, thanks. That's a lot of great detail. That's just what our audience loves to hear about. So I really appreciate that. You cannot give too much detail to our audience.
Oh, really? I don't want to go too much. I think
no, you cannot. So you're doing amazing. This is exactly what we love to see, because the only thing they don't like is there was not enough detail. So throwing in code numbers and equations and stuff, that's exactly what I want to hear, what they want to hear. So I do appreciate that. I want to get to the seismic structures that you're talking about, but it sounds to me that designing for these data centers is quite different from other structures, because you have to find out so much more about the weights and the components that normally happen, after a structure is built before you can even build it. How much of a difficulty is that? Like, can you even get started before you know exactly what's going in there and how much it weighs and where it's going to go? Like, that seems very different than normal structural engineering. Am I correct?
Um, a little bit. I mean, the thing the data centers, so what data centers are trying to do is they're trying to accelerate construction, right? So how do you accelerate the construction process? Well, it comes with planning. How do you create a good plan? Well, you need to define the components step by step that go into the structure. And so a lot of times they know what they're going to put in there, right? Because they know what the target is so that they can get the return on their investment. And so like that's what these guys are driving for, is they need to get a return on their investment, right? And so a lot of the plans and the design is done up front, and a lot of times the equipment is spec'd, because if you're designing, like when you're designing the building shell, you've got to make sure you're designing the slabs on grades for the 250 PSF or 300 PSF live loads that they need for all of this equipment. So yeah, so I mean that it's actually defined pretty well up front.
Okay, so as these weights seem, are they more standardized than I think, so that you kind of have a much better estimate and guess than it's not
Yeah,
just okay. That
yeah,
that makes some sense to me. All right, now I'd like
yeah.
to kind of talk about the seismic aspect of all of these and the anchorages you're talking about. Can you go into some details about what the concerns are? Are these just in areas with seismic events? Do you have to design differently for different locations? And how local is your design to your location?
hmm Yeah, good question. So, if you look at there's a seismicity map. I mean, you can look it up online, but basically, you can look at a map of how active the United States is seismically, and the West Coast is really heavy, and there's also some parts in Ohio that are pretty high. And so, for seismic, weight matters. So the heavier the item, the more inertial force there is, and there's more essential, horizontal seismic force. And so that goes down into the anchors. And so, yeah, like seismic, it really does matter. And that's basically for the whole building and for these non-structural components that are inside the building, because everything has weight, right? Um, but for the shell of the building, then as you might go towards the east, then you have like tornado issues, or like in Florida, you have really high wind stuff, or hurricanes, right? They're not building too many data centers over in Florida. It's mainly on the East Coast, further inland. But yeah, I mean, the location does matter. And the other thing is power. There's a lot of power, demand that these data centers, take up. And so that's also part of the planning. Us structurally, we're not really involved in that, but that really determines, as they're looking to develop, they're looking for access to, these resources that they need to power the data centers. And if there's a specific location that has it, even if there's seismic, they'll build it. Like as you can see out here that we have, it's called Trick or USA Parkway. There's, we have high seismic here, but they're still building a good amount of data centers.
Okay, so I guess just to pull out the picture kind of for even for maybe just me, when you talk about the weight needing to go into anchorages, what
Mhm.
exactly do you mean by that? What does that look like? You're taking these weighted systems and how do you make sure that that is distributed? Is that through, drilling and piling or I'm just curious what that really looks
Yeah,
like.
yeah. It's pretty simple. Is these non-structural components they're basically anchored to concrete slabs or steel decks. So there's a few ways that we do these anchorages. Is and like a majority of the anchorage is driven by these sort of like substructures that are inside the building. So in data centers, they have hot aisles, and these hot aisles are where all the racks live, right? And those racks have all these GPUs, and they're producing insane amounts of heat, right? So the issue here is heat, is you've got to take care of the heat. And how do you take care of heat? Well, it's through like wind cooling, right? But now the demands are getting so large because of AI that everybody's turning to liquid cooling, right? And so how do you provide liquid cooling? Well, you need fluid. And what do you need to support the fluid? You need pipes. And what are pipes? They're heavy. And so what in the seismic in the seismic country, when you have heavy things, they move in a seismic event. So now these pipes need to get supported. And so you can support these pipes to the ceiling, and you brace off up into the ceiling, and you're just tying with some anchorage. And there's multiple ways to do it. A lot of times it's like subcontractor driven, what manufacturers they're aligned with and who has the anchors that they want to use and what their crews like to do. And then you can also create essentially your own like structure that sits above these racks. And sometimes they put, they'll put these fans up above, and they'll put the liquid cooling pipes up above there too, and run them through a loop essentially. And so you need something to support that. So there's so many ways to do this. What it comes down to is like those loads need to go down into the ground, right? And so how do you get them into the ground is they need to get attached to a slab essentially, or they need to get attached to the steel structure up above and then carried out to the building down into the ground. I mean, essentially that's how buildings stand up, is they're supported by the ground. The loads have to make it down into the foundations.
So how much research do you typically have to do on a project when you've got to figure out who the contractors are, what kind of cooling system that they're looking at, what the weights are going to be? It seems like there's an awful lot of upfront knowledge that you need in order to be able to design these things.
For us, these things are surprisingly easy, because if you have the defined geometry, right, then it's actually pretty simple. Is you get the geometry and then you run it through your calculations. And from job to job, there's some nuances depending on the contractors, and this is for all jobs and in all aspects of structural engineering. Every contractor kind of has their own preferences that you have to try to align with and have them communicate to you so that you can provide a good service to them. But yeah, I mean, for the most part, this stuff's pretty basic. And the code requirements in the ASCE are, I mean, they're pretty straightforward. Going through the calculations. Like for us, it's seismic out here, and so we just hit the ASCE, we do the inputs, we do run through the calculations, and then we tell the contractor what they need. And then there's a lot of times there's a lot of back and forth. But the thing that I didn't mention before, and I was talking about planning, right, is what makes these things go quickly is being able to plan. And in the construction world, if you can create a virtual model of the building and the items going inside the building, right, using BIM, then you can essentially foresee the problems before you get to them in the field. And that is the main goal, because when you find problems in the field, you have your 20 guys in the crew standing around burning all the cash and nothing's getting done. And so that's a lot of, every single one of these data centers is highly coordinated. They have teams of BIM modelers, right? And they have high level of detail models. These are LOD 450, so LOD is level of detail models, and 450 to 500 means they're basically manufacturing level. So all the components are modeled so that you can pre-manufacture the items off-site and come in and they'll fit on site. And so that's kind of what helps a lot of this stuff out is a lot of the high level of detail modeling. And so what I was getting to is, we'll coordinate with these contractors with their models and get in and communicate things, and pictures worth 1,000 words. So like that's why you use BIM. Yeah.
All right, Joel, that's great. There's so much great information there. So we've talked a lot about kind of the work you do, but as an advice to say other engineers who, whose organizations are wanting to get into this or they're bidding for a data center project, what advice might you give to them on things that they should be thinking about, they should be looking for before they get started to maybe kind of, save them a step or two?
The main thing I would try to encourage is it's communication. Make sure you get aligned with your clients or whoever you're bidding the job to make sure that you guys can provide the value that they need. And there's a few the codes. So here's the thing: the code that I mentioned, ASC 722, is essentially just a life safety code, right? And it doesn't guarantee that after the seismic event, your components are going to be working. And so you've got to make sure you communicate that to whoever your client is to make sure that they understand that, because you could put in millions of dollars of equipment and then you get the seismic event and it doesn't work because it just got destroyed because there's too much deflection or whatever. You technically met code, but it's not operational after a seismic event. And so there's basically that's something you need to communicate up front and make sure everybody knows. And if they want the higher standard of care, then you can provide a higher standard of care. So California has in California, OSHPD is the essentially the building department that oversees the hospitals and the schools. And so they've come up with a different procedure or a different code. It's a little more strict than the ASC 722, and they have requirements in that code for exactly that. Is the operational the equipment needs to be operational after the event. And so, yeah, I mean, if that's something that the client's interested in, like, you could potentially communicate to them, and that's like how you provide value to your clients, is like communicate this stuff up front, and then if they need a higher standard of care, then you can go down that route and obviously increase pricing. And so you could have different tiers for pricing, as code compliance, ASC 122, or a higher standard of care. Following the it's called ICC-ES AC 156. That's basically a shake table test that you can do with your equipment. They'll guarantee it's operational after the fact. A lot of equipment manufacturers do this. So that's one thing. And then as it relates to anchors, yeah, I mean, for the anchorage stuff, you could still use the code minimums, but I just want to make sure that when you're getting into this, you communicate to the end user, hey, like, sometimes this might not be operational. Always communicate with your client and make sure that you guys are aligned.